excuse me. As I said, the most important thing is burner to burner spacing for uniform. More burners will give lower heat release rate and uniform heat transfer, shorter flame lengths. Any flame length more than 10 feet is not good. 10 to 12 foot, your flame length should be limited to 10 to 12 feet. If you want to see the flame lengths in your furnace, go to a drugstore or grocery store and buy a pack of baking soda. You can put the baking soda through the peepholes or through the air registers, and you will really see the size of your furnaces. The low NOx burners flames are generally invisible because they are a low temperature flame, so you are not able to see it. The best way to see it is in the night, and try putting baking soda. And we can definitely help you in reducing the flame size and improving the run length or high tube metal temperatures. So we have developed a heater coking index using this 7 parameters, and our objective is to achieve lowest possible coking index. That's what we are trying to achieve. We have radiant heat flux, mass velocity, coil size, burner heat release, burner to tube spacing, burner to burner spacing, and burner air side pressure drop. I think I've already repeated most of these. So again, burner to tube spacing is very important. And if you have a heater which is already there and you want to increase the burner to tube spacing, use our inclined firing technology. When you use our inclined firing technology, you can increase the burner to tube spacing by 1 to 2 feet depending on your furnace, and that will contribute a lot. We have done projects for Citco and Valero and other people where we have reduced the tube metal temperatures anywhere between 100 degrees F to 250 degree F. So you can see the power of burner to tube spacing, and our inclined firing technology is most suitable if you are having high tube metal temperatures. We can reduce the tube metal temperatures and scaling on your tubes. So these are some of the parameters on the run length. I think I've already talked about it. So I don't need to go over it again. Average radiant heat flux, yeah, they are already talked about it. Similarly, I've also talked about most of these parameters. You want to achieve lowest possible tube metal temperatures, and whatever it takes, whether it's an existing heater or a new heater, I think you can definitely put new burners or put them at an inclined firing so that we can increase the burner to tube clearance. If you have a heater and you are looking at improving the run length, here are some of my suggestions. Go for maximum excess air in the heater. Increase the excess O2. If you have a heater which is suffering from high tube metal temperatures, you can increase the excess O2 to the maximum, and that will help a lot. Light all burners. If your burners are not lit, you're only lighting 50%, light all the burners, and that will reduce the flame size. And both these actions together will cool the firebox, shift the heat to the convection section, and you will get more heat transfer in the convection section, lower tube metal temperatures in the radiant section. So this will also help you get better run length in existing fired heaters. This is a comparison of a crude heater with what we designed as compared to the average design. And we are trying to show you how the coking index, we were able to lower the coking index from 70 to 1/5, almost 14, and that is how we achieved 8 years run length. So if you have any doubts, but it is pretty simple, contact us if you need any help with the run length or design of new heaters. We will be able to help you out. We received a question about best practices for fired heater design. I think I've already talked about most of these parameters. One thing which I want to talk about is margin on heat duty. I have seen in number of installations, the inlet temperature to the heaters is much lower, and the culprit is not the heater, the culprit is the preheat drain in front of the heater. If that is fouled, the inlet temperature goes down and the poor heater has to bear the brunt and go for overfiring. So when you are designing a heater, best practices, put a margin. Find out what will be the lowest preheat temperature if your exchanger train is fully fouled, and use that temperature to design the heater. You don't build heaters every day. The life of heaters is anywhere between 20 to 50 years. In fact, I have seen heaters which are even 70 years old. So put a margin on heat duty and design it for the worst case so that you never run short on heat duty. And that way you will get the best heater. It won't take much. I mean, if you have to put another 5 million BTUs or 5 million kilocalories in the add to the duty, it won't cost you much. And then if you have any doubts, you can hire Furnace Improvements and we will provide the best heater design for your project. We can do that, and I assure you. This is a CFD model of inclined firing, and you can see over here how using inclined firing, we keep the high temperature hot flue gases within the furnace, within the center of the radiant section, and lower the tube metal temperatures. On the left-hand side, you can see flame impingement on the tubes, hot flue gases impinging directly on tubes, and that has been eliminated, and we have been able to lower the tube metal temperature substantially. So one question we had is, how do material selection for fired heater tubes is done? There are two ways to do it. One is the process consideration, and the process consideration comes because of corrosion and the fluid which it is processing. So that is one way to do that. And that is normally specified by the process engineer. Maybe the crude has naphthenic acid or some other component like H2S or sulfur. So they will specify the minimum metallurgy required from the process side. And then the heater engineer looks at the temperature side and looks at what is the maximum tube metal temperature. And we design the tube for 100,000 hours. So we calculate the thickness and select the material. And API 530 gives a very, very good guidance on material selection and tube thickness calculations. It's been accepted worldwide for last 70 years, I would say, if not more. So the factors are like operating temperatures, oxidation resistance, sulfidation, creep rupture strength, So there are typically two designs. There are elastic design, which is a low temperature design, and then there is a high temperature design, which is a creep rupture design, and whichever is controlling dictates the thickness. I've been asked a question about NOx reduction technologies. So NOx are nitrogen oxides, which are harmful for human health, and they are formed during combustion. There are two ways of handling NOx reduction. One is known as pre-combustion technologies. These are more popular, where we use ultra low NOx burners or FGR for reducing the NOx. And then the second way is post combustion. We let the NOx form and we try to remove the NOx using a catalyst, and then it is known as selective catalytic reduction unit. Or the other process, which is more popular in boilers and not so much in heaters, is SNCR, selective NOx uh, selective NOx reduction unit. So SNCR is normally used in boilers. SCR is mostly used in fired heaters. It's a catalytic process, and what we are doing is we are taking ammonia, injecting ammonia to react with NOx and get reduced to nitrogen. That is the process the reaction which takes place in presence of a catalyst. The approximate temperature is around 650 degree F or 350 degree C, 350 to 400 degree C. That's where the temperature takes place. So I think it's a very good technology. It was first developed in Japan, and it can be installed upstream of air preheater, especially in India, where we have a number of air preheaters installed. So this technology can be installed, the catalyst bed can be installed upstream of air preheater and can lead to NOx reduction. NOx reduction is done predominantly by pre-combustion, but you are paying a price. The price is any reduction in NOx comes at the expense of the flame length. You want lower NOx, you will have to go for a higher flame length, because lower NOx means bad mixing, delayed mixing, fuel staging. So all these things will reduce NOx, but they will increase the flame length. And higher flame length will cause you more problems, will cause you high tube metal temperature problems. So beware that if you're going for low NOx burners, be prepared to face problems of high tube metal temperatures. Typically, low NOx burners have twice the flame length of standard burners. So just think about it. If you have standard burners with 10-foot or 12-foot flame length, and then what happens if the flame length goes to 25 feet? It will do nothing but impinge on the tubes. That's a low tube metal, range actually. So it happens very, very often. So I'm not scaring you off. I mean, low NOx burners have been installed in hundreds or thousands of heaters, but just be prepared to see. Another thing which is happening recently is talking about greenhouse gases. We are talking about reducing the carbon footprint, reducing the emission of carbon dioxide. It has been talked a lot because carbon dioxide is a triatomic gas and it's responsible for global warming. So it is coming, may be coming now, maybe coming in 5 years. We will all be forced to reduce the carbon footprint. Some of the things which we can do here is increase efficiency. And when we increase efficiency, we reduce the carbon dioxide emission. All I can tell you is in US, 90% of heaters are natural draft, so there is so much potential there to reduce the carbon footprint, improve the efficiency, and I'm thinking these things will continue. Other thing is switch to hydrogen-rich fuel gas. Uh, it will happen, but hydrogen is very expensive, and actually methane is used in manufacturing hydrogen. So if methane continues to be used in manufacturing hydrogen, we are really not reducing the carbon footprint. We are just using one source instead of another. We are shifting it to methane instead of the fired heaters. Reducing excess oxygen will also improve the efficiency, so it will reduce the carbon footprint. My colleague has prepared this. What happens when we switch from natural gas to hydrogen-rich fuel? The carbon dioxide percentage goes up by about 1.5%. So it does make an effect. I mean, this is 64% hydrogen fuel. If you go for 100%, then of course we will eliminate carbon dioxide completely. So how does hydrogen in fuel influences the design of fired heaters? Hydrogen is a very good fuel, very clean fuel. Hydrogen, here are some of the things which my colleague has put. Hydrogen, the flame speed is 10 times that of methane, So it burns very fast, very, very fast, and helps in reducing CO2 emissions. The flames are clean, the flames lengths are shorter. So I think if you're really burning hydrogen, you will be not having many of these problems. Of course, everything has to be optimized. The burner will have to be checked and made sure that it is suitable for firing 100% hydrogen, because hydrogen density is much lower. So now if you're processing 10 times the volume from the same tip, the pressure drop will go up. Your fuel gas pressure will go very high, so you have to see whether you really have that header, or you have to change the tips to get to the lower pressure. So these will be some of the things. So I do have a few more issues which our participants had talked about. High arch temperature, very, very common problem. I also want to tell you that it is very difficult to measure the arch temperature correctly. And if you ask me, you should measure the temperature in the convection section, at the inlet of convection section, because that's where the flue gases are flowing. In fact, we received one question which talks about that they are experiencing higher temperature of flue gas after the arch. Our experience is arch temperature is anywhere between 200 to 300 degrees lower, 200 to 300 degrees F lower than the actual temperature. So measure it in the convection section, at the inlet of the convection section, if you really want to get good. Or use a velocity thermocouple. If you want to put it in the arch, then use a velocity thermocouple. Next is high arch pressure. High arch pressure, again, a common problem, and it indicates two things. One is your convection section is plugged, or you are firing very hard. So one of the two things. So if you are experiencing high arch pressure, it is not safe also. If you are experiencing positive pressure, it is not safe. So reduce the firing rate and try to clean the convection section. See if your stack damper is fully open. Sometimes if your stack damper is not fully open, you will experience high arch pressure. High excess air, that's another issue we have seen. Even though all of us are targeting 2 to 3% O2, we often see 7 to 10% O2 in many heaters. It could be due to high draft. It could be due to uh, leakage. It could be several, reasons. But I think it should be possible to reduce excess O2 down to 2%, and that will help the operation tremendously. Will reduce your fuel consumption tremendously. So look at this. If you need any help with any of these operating issues, contact us and we will always help you out. So what are the best design and operating practices for fired heaters to achieve high efficiency and low emissions? I think I covered most of it in the limited amount of time. We will continue to get your questions and keep on answering them on Facebook, LinkedIn, our website, and future webinars. I was talked about what are the best ways to measure tube metal temperatures. Uh, our suggestion is tube skin thermocouples. There has been tremendous improvement in tube skin thermocouples, and they are very reliable and inexpensive. So try to go for as many tube skin thermocouples as possible, maybe 4, 5, 6 per pass. That would be our recommendation to monitor. We don't want you to lose a tube or have a tube rupture. So if you are having high tube metal temperature, put more tube skin thermocouples. You can also go for infrared thermography. There has been tremendous improvements in infrared thermography. In fact, I was told that there is an attachment now available for iPhone. I know it will not be allowed in your refinery, but they have come up with an attachment which you can put on your iPhone, and it will become like a thermography, instrument. So there have been a lot of improvements. You can do infrared thermography. A lot of companies do it for you, and you can really see what is happening inside the furnace. So I've received a question on high emissivity coating in helping improving efficiency and tube life. It does help marginally, but we have not seen any substantial improvement. I mean, what we will suggest you is sandblast your tubes, remove all the scales, and you will get the same benefit of that you will get with the emissivity coatings. The high emissivity coatings are very expensive. You need to do them every 3-4 years. I don't see major benefit. I want to attack the root cause of the scales, and most of the time it is the burners. So if you can fix the burners once for all, then you won't get any scales on your tubes and you won't need any high temperature coating. So with that, I want to thank you all for your time. Send us more questions and we will try to organize another question answer session, maybe on Zoom next time, so that I can see all of you and maybe talk to you. So thank you once again. Bye.